So now I will talk of one more very important concept, which is this thing about conditional independence. So consider some three events A, B, C. With, let us say, P, C alone, we are interested in conditioning on C, where if you, I'm not going to keep on saying it, maybe say it maybe one last time, right? Any time you condition on an event, you assume implicitly its probability is non-zero, right? So A and B definition, right? A and B are conditionally independent given C. If what? P of AB given C, this intersection probability given C can be written as P of A given C multiplied by P of B given C. Note that this is not the same as the absolute or unconditional independence of A and B, right? So this is not equivalent to P of AB equal to P of A into P of B. The two are not the same at all. You can have one without having the other, right? But if you want to simplify this, you can, there is no reason why you must write it only in this form, you can write it in some alternate forms also, right? So for example, this will become P of ABC divided by PC equal to P of AC by PC by times P of BC by PC, and you can knock off one of these PCs and write this in some other way, right? You can manipulate this to write it in some other which I am going to let you do, right? It's not very important. I'm just from a manipulation point of view, right? Nothing stops you from simplifying, right? And you can take one of these down here and look at right, if what is P of ABC divided by PPC, assume this is positive, right? If this is positive, you can divide by this and put it down here. P of ABC given divided by PBC is nothing but P of A given BC. So i.e. this means that P of what? A given BC is going to be equal to what? What you will be left with is AC by PC, which is A given C. Okay, maybe I didn't need to write the whole thing out, but so this will imply this, and this also will imply this in the case that both BC and C have positive probability, right? Of course, if BC has positive probability, C will definitely have positive probability, right? So basically it's right. So this is another way of writing the same thing, but typically, they don't do this manipulation, they just stick to this more right, a simple definition like this, which you can easily remember, right? Anyway, but remember, these two are definitely not the same at all, right? Now where do you encounter conditional independence in practice, right? We go back to our communication channel that we talked about yesterday. So an example of conditional independence, supposing you have multiple uses of this channel. Let us say this is 0 sent and 1 sent, right, and 0 received and 1 received. This is 0S, 1S, 0R, 1R, right. So it turns out that in many cases, right, the memoryless channel means that successive transmissions are independent, right. So this memoryless channel means what? Independent transmissions. So when independent transmissions, when transmissions are independent, then what do you say? So this implies that the probability, for example, of supposing you send, given let us say 101 is sent, right, and let us say you are looking at the event that the same 101 was received, right, the whole thing is fixed. We have already said that, right, in our discussion now we will assume the whole, right, we can only take measurements and we can't change our decision rule or whatever, right, everything is fixed about this. You know that you can send a 0 and receive a 0 or receive a 1 also, right. So all of that is fixed, right. So this probability of 101 received given that 101 is sent. So here now you are freezing the input sequence. So how does conditional independence come into the picture now, right? Given this sequence was sent, if the channel is in fact memoryless, right, then you would write this, the probability of this conditional probability as what? As this would be like AB given C, right, where AB is what? Receiving, in this case it is ABC, that means, or sorry, the ABD, whatever, 3 events I am talking about, right. I am talking about 3 different transmissions. So this would be the probability of 1 R given 1 cent multiplied by the middle one, which is 0, right, given 0 cent, and then again another 1 R given 1 cent. Note, of course, I could have a different sequence here. I could say, well, what is given the same input 101 cent, I could have, let us say, just say look at 000 or 111, whatever. All I would do in that case would be replace these 3 guys while keeping this one fixed. So in a memoryless channel, right, acts independently on each bit. It does not care about where the bits came from. So this is basically an example of conditional independence. But if you looked at, right, if you looked at the overall probability of getting 101, that will not be equal to, in general, right, probability of receiving 1 multiplied by the probability of receiving 0 multiplied by the probability of receiving 1 again, because these 3, that would depend on the prior probability that you would attach to, or the sequence 101. Supposing, for example, right, the same input bit 1 was mapped to the sequence 101, some coding was done, right. That is an example of a simple example of coding, right, where you are sending more bits than is actually needed. Then in such cases, right, clearly, right, the probability of receiving, probability of receiving 1 and probability of receiving 0 and probability of receiving 1 are not independent. They are not independent events, right. This will not be, right. So in general what I am saying is that, what am I saying? I am saying 101 received is not equal to the probability 1 R probability of 1 0 cent, sorry, R into probability of 1 received. Okay. So because I am not, right, this one requires the input, right, it requires this overall probability requires you to know how the input sequence 101 was formed. This one does not. This one looks only at transmission. This one is a combination of both the transmission and the input and prior probabilities. This one requires only translation probabilities, right. So if you know, for example, these 0 given 0, 1 given 0, those things, it's enough, that's enough to write this guy out, whereas for this, that's not enough. Is that clear? Any questions on this? So this is an example where you do have conditional independence, but you don't have overall independence of the received bits, right. So we have come to the end of today's class. We will continue tomorrow with a different topic. I am going to speed up, right. We are going to revisit this example that we did yesterday in a bit, so we did it quite fast. So this memoryless channel, right, basically it does not remember what it did. So if I have 0 cent, 0 or 1 cent and 0 or 1 received, as per yesterday's notation, what did we say? Okay. So what is so if I want to say 0 0, so let me put some numbers here or whatever symbols. So this small p will represent the crossover probability, right? Probability of receiving 1 given 0 and receiving 0 given 1, right? So that these are 1 minus p and 1 minus p. I think yesterday did I put any, did I use this notation or not? No, okay, so let's use it today. So that if I have if I want to look at this probability of 0 0 received given 0 0 sent, right, just for any two, right, two instances, two transmission instances. So this is going to be 1 minus p squared, right? How do I get this 1 minus p squared? Is 1 minus p times 1 minus p. If I want to look at, let's say 1 0 received given 0 0 sent, it will be p times 1 minus p, like that, right? So that is a property of a memoryless channel, right? Each transmission is independent of any other transmission. The channel doesn't care. This is a channel model and doesn't say anything about how you get these symbols in the source, right? Is this clear? Okay. Now if you want to look at, right, the probability of receiving 1 0 and then another 0 after that, those two events will not be independent, right? So you can see that this is let me write it even more explicitly. 0 0 received given 0 0 sent is a probability you have 0 received given 0 sent multiplied by the probability of 0 received, another 0 received given another 0 sent. These two of course are the same, right? So that this is how the channel works. But if so, you can say that the bits are independently transmitted by the channel, right? You have this is a version of conditional independence that we talked about yesterday. However, if you look at the probability of receiving two zeros in succession, it will not, those two events will not be independent in general. You see what I mean? This will not be the probability of 0 received squared. So this is a case of conditional independence without, right, without in some sense absolute independence, right? Now why is this happening? This is happening because you don't know how you are forming the input bits, right? Supposing, right, I am looking at this 0 0, as I said yesterday, this was a coded version of an input 0. That is, supposing an input 0 or 1 was chosen independently with probability half, right? That part can be independent, but supposing a 0 is sent, right? 0 is sent as 0 0, and then a 1 is sent as 1 1, right? This is a simple example of a repetition code, right? You're introducing redundancy just to improve the performance, the reliability of the communication channel. It turns out it's not a very good thing to do, but it's one of those classical examples that is taught first in the classroom to illustrate how, right, you can use, you can sort of lower your bit error rate. Of course, you wouldn't want to repeat it an even number of times, you'd repeat it an odd number of times, right? And you take a majority count or something in the receiver to figure out which was actually sent, right? So, but anyway, we're not going that far in this course. We're only looking at, let's say, just the simplest version, which is just repeating just once, just to prove the point, right? Now, supposing your 0 and 1 are equally likely, right, the input bits 0 1, let's say they are equally likely, that is, probability is half. Then what is the probability of receiving a 0? This that is, what is the probability of receiving a 0 no matter with just one use of the channel, right? Then which this will imply the input bits are equally likely. The probability of receiving 0 is what? you can show that it is half into 1 minus p plus half into p. How did I get half into 1 minus p plus half into p? This is just for using the formulas or whatever we did last week, right, or when the early part of this week. We condition on the input bit being a 0 or 1 and write this out. So this is going to be, what is this going to be? This is half, isn't it? But what is the probability of getting a double 0? This same 0 is being sent as a double 0. So the probability of sending a double 0 is also half, right, because you are repeating that 0, right. So probability of receiving double 0 is basically, right, you have to write this as probability of 0 0 given 0 0 plus or times the probability of, this is the input, right. You can also get it with 1 if the bit were 1, but you do not have this combination of 0 1 and 1 0 at the input, because you are sending, you know, each bit is being doubled before being sent, right. So you do not have the combination 0 1 or 1 0, right. So you only have this. Now you write this out. This is going to be this 1 minus p squared, and this is half, because this is the same as this input bit 0, which, right. I am looking at, right, suppose you are looking at a single one or transmission of a single input bit which is sent as a double 0. So what is the probability that received sequence is another double 0, right. The input bit could have been just as well been 1, in which case 1 1 would have been sent, but you can still get 0 0. So this is the probability of, therefore overall probability of getting this double 0 is 1 minus p squared multiplied by half, right. The probability of sending this is half. What about this? P squared into half. So this is not equal to half times half, right. Right. In general, it is not equal to this, especially if p is high, right, very close to, you would like this p to be what, very close to 0 actually, right. So if you say, if you are allowing a small value of p, for example, right, you can easily see that this is not going to be half squared. In fact, if p is very small, it will be close to half, not half squared, right.
Why are we not taking 0 1 and 1 0?
Because those combinations will, you know, I am looking at after the coding 0 sent as double 0, right. I am looking at the event, I mean looking at the transmission of this coded bit 0, which is coded as 0 0. So and the reception of that can either be received as 0 0 or 1 1, but the 0 0 can come also from 1 being sent, which will be sent as 1 1, but the channel does not know about the coding, right. The coding is done independently of the channel. The same channel is used for all the coded bits independently, right. So that is a conditional independence which is imposed by the channel. It is a memoryless channel. Those of you that want to study information theory, you better take this example very seriously, right. I do not know how many of you out there, right, want to get into the wireless information theory business, but for all of you, all those students, right, this kind of stuff is a basic right, starting point, right, the discrete memoryless channel as they call it out there, right. So there you have, right, any regardless of any coding done on the input bits, right, the probability of a string of bits being received given a certain string of bits being sent, you can write that for a memoryless channel in terms of individual transmissions. What is the probability of 0 0 received given that 0 0 1 was sent? Is, you can write it out, right, in terms of the individual transmission. It means what, 0 to 0 0 to 0 0 to 1, whatever. You can look at the patterns of the input and output and figure out how to, and all you have to do is multiply out the, right, the various conditions that are happening there, and you get the right for this block of bits, this is the output block given this particular input block, right. You can write it out just by multiplication. So that is conditional independence without the independence in the deeper sense of, is this probability of getting a 0 in the first as the first bit independent of the 0 in the second bit. It is not. That is what we are showing here. Okay. So this is a more real life, more electric communications, I should say, example, inspired example, rather than taking coins and flipping them and so on, right. Although the same mathematics can be made to apply to that setting also, but I think this is a nicer way to understand, right. So I think this should be sufficient to explain it.